In this video segment, I'm going to be showing you how to calculate the stress wave propagation characteristics of a, a bar that is impulsively loaded in 3D Experience Release 2022x. Now, I will be using implicit dynamics to do that. The problem under consideration is a bar like so, which is impulsively loaded at one end uh, as indicated here. We will be solving the problem as with bar elements or beam elements, but it can be done in other type of elements such as shells and solids. But here we're going to do bar element. We are assuming that the cross section of the bar is 1 square inch. Because it is a bar, it really doesn't matter what the shape is. What is important is the actual area cross section. Now, 20 inches long, this is not drawn to scale. The Young's modulus is that of steel, and Poisson ratio is going to be taken to be zero because when you use bar elements or beam elements, Poisson ratio does not come into the picture anyways. Density is given in this rather unusual unit, imperial unit, slinch per inch cube. And these simpler videos are intended for people who want to learn, practice with the FEA solver, native FEA solver of the 3D experience, which is in a sense Abacus standard. Okay, so that's pretty much it. Okay, so the bar is impulsively loaded, and that means that you can think about it as no load, and then suddenly jumps to 100. It's as if you hit the end of the bar and hit it with a hammer and kept it at that value, 100 pounds. And when because of this, a stress wave is going to propagate through the bar. The speed of propagation of the wave, that compressive wave, is given by E over rho. Now, here's what's going to happen. And this is going to be the stress value within an element in the middle of the bar, halfway point from the two ends. And it's going to look like this as a function of time. I will have a discussion about this towards the end on what does this mean. By the way, these are the values that I'm going to be using for the uh, implicit dynamic step. This is the displacement of the middle point of the bar. Notice that there is no displacement up until some time where the wave actually reaches that. And then it goes to the left, gets closer to the wall, and then we will talk about this thing later on. And here is the different stages of the stress wave propagating through the uh, through the uh, through the bar, and it's showing you the value of the stress at the middle point, middle element of the bar. So you can see that there are some instances, there are some times where actually that middle element of in the middle of the bar, there is no stress. And sometimes there is a stress of 200, compressive. This has to do with the stress wave propagation and reflection from the hard end, which is the wall, and the soft end, which is where there's no restraint, where the load is applied. Okay, let's go ahead and do this. I'm going to start a part file. Very simple model. We're going to create 2 points. One at the wall, basically 0, 0, 0 inches, and another one which is 20 inches away, the length of the bar along a y direction. There we are. So these are my 2 points. And then I'm going to create a line between these 2 points, this point and that point. And if you want to see the bar, you can zoom in, or you can say view and fit. There we are. And I'm going to hide these points because I don't want at some point inadvertently put loads and restraints on these. Okay, let's create our material. Under tools, create a material. We'll call it stress wave. Stress wave video. Okay, we say apply. I'm going to apply this, right click, apply, close this, I don't need it, apply it to that part, green check mark, and now we're going to input the values. So we go here, double click under structures, general, density, it was 0.3073 slings per inch cube. Okay, takes care of this, and then we're going to go to abacus multiphysics, mechanical, elasticity, elastic, 30 million psi, and 0 Poisson ratio. So 30, 30, and 6 zeros. So 1, 2, 3, 4, 5, 6. A 0 Poisson ratio. Okay, good. Now we're going to go and mesh this. We'll mesh it with 40 elements. So it's going to go structure model, empty FEM. That means because you have to use beam elements or bar elements, you're going to have to do the meshing yourself. So here under mesh, there is the beam element. 40 elements, that means the length of this thing being 20 inches long, is each one is 0.5 inch. So the support, here's the support, and mesh it, say okay, there's 40 elements along this. Now, cross section of the bar or properties of the bar. So click on properties, select the link element. The support is that bar, and cross sectional area is 1 square inch. Material is properly selected. Now, this thing is bothering me, so I'm going to hide that. Okay, there is our beam. Now, we are going to need two groups. One of them is a group which in it has the node at the middle, because I want to get the displacement of the middle node. Now, since we cannot do this without creating a group, or we cannot just select a node and say, show me the displacement of that, I'm going to create a node group, which in the Abacus program is called node set, of course, and an element group, which is the element in the middle, somewhere in the middle, and that would be the equivalent of element set in Abacus. So let's go to groups, manual group, and somewhere in the middle here. It really doesn't have to be exactly in the middle, but I'll call it midpoint, middle point, middle point. And we already selected. Let's do another one. Here is the first one that I created. You can see that. Do another manual group, but this time I'm going to select element, not element face, element. Okay, so element is one of these elements in the middle, roughly in the middle, and I'm going to call it middle element. Middle element. Okay. All right. So middle element right there. Now we're done here, so we're going to go to structural scenario creation. You select the finite element model that we just created, consisting of those nodes and elements. Okay, and now we're going to go to procedure, and we're going to do implicit dynamics. Implicit dynamics with those numbers that I showed you right here. You see this? Now this requires some thinking. In other words, am I taking it to be too big, too small? Basically, you want to choose the time so that the wave travel a few times. If you make it too short, the wave never reaches the end. If it makes it too long, there's going to be too many of these, etc. So these are the values that I'm using, and you can experiment on your own. So let's go back here and plug these things in. So this is going to be, let me see, 4e to the minus 4. 4 e to the minus 4. Okay. Uh, I'll use as a safety 10,000 or 1,000 points, 10,000 points. It really doesn't matter because this is just a maximum number. And here I will use for the initial time step 1 e to the minus 7, e to the minus 7. For this one, I use 1 e to the minus 8. And for the maximum time step, I will use 1 e to the minus 6. E to the minus 6. Okay. So now, the one thing you have to realize, this is assumed to be a small displacement really. So I don't have to include geometric nonlinear. You can. It really doesn't matter. It doesn't hurt you. But I'm going to uncheck it. Okay. So because I know that the strains are going to be small, displacements are small, materials linear elastic. Therefore, there's no reason to include those nonlinear geometric effects. Okay. Now. Restraints. So restraints, I want this thing to be axially loaded. Therefore, I'm going to select this entire line and says don't move in the direction X and don't move in the direction Z. Rotations are irrelevant because these are not degrees of freedom for link elements. All right. Now, to prevent rigid body motion, this endpoint, this is going to be the wall. Okay. I'm going to say don't move in the direction Y. Already it's not moving in X and Z. Rotations are irrelevant. There we are. Now, as far as the load is concerned, I'm going to select the force over here in the direction y minus 100 pounds. Now, notice that amplitude says default because default means that the load is going to stay like that. If the load is varying, like the previous two video segments that I did on implicit dynamics and modal dynamics, there, of course, I had an impulsive type of load with a triangular shape. It was not constant. But here, I'm assuming it's constant. You can see in the drawing right there. So I'll use default. I mean, obviously, if you wanted to make your own tabular amplitude, it's going to be a horizontal line, but there's no reason to do that. Okay, so that's pretty much it. Good. Now, before I run it, first of all, let's go to Simulate tab. Before I run it, I have to ask for data. The question is, what is that data? I want the translation of that middle node group and the stress in the middle element group. So I go here, I go to this output. Okay, so I want to do it by groups. So for middle node right there, I wanted the history output, not the field output, and I want displacement translations. Translation direction 2 is good enough because it only translates in direction 2. Okay, at every increment. Okay, then another one is going to be again group. This time it's going to be middle element, and it's going to be history output, and I want stress, and I want all components of stress. Okay. In this case, there's only one component of stress. That's the axial stress. Okay, but you know, I asked for everything. That's pretty much it. So let's go ahead and run it. So first of all, let's do a model and scenario check. Any obvious errors are going to pop up here. This is okay. And then we do a simulation check. Again, any obvious errors are going to appear here. Finally, we're going to run it in just a minute. Notice that I ask information for at every increment. If there are many nodes, many elements, and you ask information at every increment, that may take a lot of storage. So, but this is a simple problem. It really doesn't matter. Okay, good. So this one went through without any errors. And finally, we're going to run. This is the actual run. Simulate. Okay. Once we get this thing, we're going to plot the middle node displacement and a middle element stress. Almost done. It's going to extract the results and then we can look at our plot. By the way, this example of taken out of a book by Robert Cook, Concepts and Applications of Finite Element Analysis. You may want to look at it if you wish. There's nothing complicated there. Okay, so these are the stresses at different instance in time. You can see that, and you can see, by the way, as time goes on, some of these elements will develop stresses. Some do not have any stresses. Okay, good. So now we're going to go to plots, history plot from history, XY plot from history. And if you expand this variable, at the very end, you see that there is translation. Okay, and I'm going to do component 2. Already asked for component 2, so that's good. Apply. So what you see here is the displacement of that middle node as a function of time. You can see that up to a certain point, time, that middle point does not even move. Then it's going to go to the left. Then the wave is going to hit the wall and return. Okay, so it's going to push it to the right. Push it to the right, and then eventually it moves up. Okay, so that's this. Let me uncheck that, deactivate. Yeah, good. So let's go to the other one, which is the stress. So you go to stress component. Notice that it only gives you stress component 1, 1 because it's a bar element. There's only one component of stress. Apply. Right here, probably. Yeah, there we are. So this is what you see there. Okay, here I have drawn also the displacement, which is this axis, but the one that we're concerned about is that stress. So this is what happened. For example, that middle element, up until some time, and that some time is actually based on uh, this speed, okay, the speed of propagation of the wave, up until some time does not see any displacement, does not see any stress because the wave has not reached there. And then the wave reaches there, it puts it in compression, 100 psi. Then after some time, that wave reaches the wall and it's going to get reflected, does not flip, by another compressive wave. So the original compressive wave, another compressive wave, they add up to 200. Then it passes through that element and it acts as that reflected wave acts as a tensile one. So it adds plus 100 to this minus 200. And then at some point, it reaches, that reflected wave reaches the free end where the load is applied, and it's going to get reflected again, but this time the sign flips. Okay, so you can see that the stress is going to go back to 0 in that middle node. Anyway, this kind of explains for you how the stress wave propagation in a very simple problem can be done with the 3D experiences implicit solver. Good luck.